All right, good morning, everyone. Welcome to this presentation. My name is Julien Didisheim, and I'll be talking about project optimization in UEFN. First, a bit of an introduction. I am a technical artist at Epic Games, and I've been at Epic for roughly 4 years now. I am based in London and part of the London Innovation Lab. So the lab is mainly focused on supporting and working with external clients from different industries such as film, advertising, automotive, or fashion. We also get the chance to work on internal projects here at Epic, and here's a few pictures from our office in central London. So I'm showing you here a panel of projects on which the lab have been involved in the past. As you can see, it goes from film, virtual production, to UEFN experiences. Technical artist, right. Even though my title says I am a technical artist, I am way more on the artistic side of things than the technical one, being specialized in design, modeling, texturing, environment building. I've got a background in traditional art and game art, and I've made my career in the gaming and advertising industry using Unreal Engine as my main tool. Most recently, I've been using UEFN to create games and experiences for a little bit more than a year now, so that's even before UEFN was released. So what can you expect from this talk? Well, first of all, I am not an engineer. So in this presentation, I'll talk about optimization, but from an artist's point of view and how you can use the different tools in UEFN. I'll explain what optimization means in UEFN, and we'll identify what to optimize and how to optimize it. And then finally, I will be timing the UEFN technical restriction and how to work with them instead of seeing them just as restrictions. To illustrate my presentation, I'll be using a project that I've worked on called Nike Airphoria. It was released in Fortnite last June and allowed players to discover the world of Nike Air. It was created by a collaborative effort from Nike, Epic Games, and Beyond Creative. So this project was a real challenge in terms of optimization, simply because of the size of the island and the amount of details we've put, as you can see in these renders. So really, the goal of this talk is to give you the keys to ship your content smoothly in UEFN and across all different platforms and hardware. But first, let's start by explaining what optimization means. And a first definition that we could give is that game optimization refers to the process of improving the performance, efficiency, and overall quality of a video game. And the challenge of a good optimization from an artist's point of view is how to keep the visual quality against the allocated memory size and the performance of the experience. In other words, for an artist, the optimization challenge is how to get your art looking like this rather than looking like that at the end of production. So now that we understand optimization, let's look at what optimization means in UEFN. And in UEFN, we can really establish 3 main pillars that we'll have to optimize to get a smooth experience in Fortnite. First, we've got the project size, which is the data size of the island. Next, we've got the memory usage, which is a memory limitation to guarantee that the island can be run across all platforms. And finally, we've got the performances, which are simply the frame rate per second that you will get while playing the island on different hardware. These pillars can also appear as restrictions, because without getting into too much details now, the project size is limited to 2 GB of upload size and 400 MB of download size. And the memory usage is limited to 100,000 units. So, and also, the performances, just like any video game, if you get some bad FPS, you'll get an unplayable experience. And we can really call these pillars some sub-restrictions, especially the project size and the memory usage, because if these two aren't cleared, you will not be able to publish an island in Fortnite. But the good news for us is that UEFN has been designed from the ground up to simplify the process of making a video game. By imposing these restrictions, UEFN simplifies publishing across all platforms. And we're also using simplified optimization tools compared to something like the Unreal Engine. Fortnite, as a game, is a very efficient one, and that will help us along the way. And finally, UEFN comes with a huge asset library containing static mesh of all sorts, which are optimized and game ready. So what's not so easy then? Well, things get a little bit more complicated when you start bringing custom assets. And when you're creating something as complex as Airphoria, you are going to have to do an optimization pass. So understanding these restrictions is critical, and you'll have to adapt your ideas to them. And finally, remember that UEFN is still in very early development, and there are still some missing features, and especially when it comes to optimization. So once again, it's important to remember that these restrictions are here to improve your game and simplify the publishing. They make sure you're not going overboard with content and improve the quality of the experience for the player. Right, let's start by talking about project size, and it is the first pillar in our UEFN optimization chart. The project size contains two data that we have to look at, but they are heavily linked. The upload size is the size of the custom asset uploaded to the content browser of a project, and it is limited to 2 GB. When you launch a live session, your data will be automatically cooked, giving you the download size, which is the size of the asset downloaded in Fortnite after being processed and cooked. On the contrary, the download size only calculates assets used in the level, and it is limited to only 400 megabytes. For those realizing that this tiny megascat rock here in the corner could fill half the 400 megabytes of download size, you are absolutely right. And it might sound terrifying when you come from UE5 and the beauty of Nanite. But remember, all these experiences have been created with the UEFN restriction of the 400 megabytes. And just so you know, a Nintendo 64 game was created with a maximum of 64 megabytes. So we got tons of room. All right, how do you visualize the project size? Well, first, we need to launch a live session to play the game. UEFN will then launch Fortnite and automatically cook your content, giving you both the upload and download size. So once the session is live, you can visualize it by clicking on the project size button in the viewport, or by going into the project size. And we want to pay attention to both the upload and download size visible at the top of the screen. In the case of Airphoria, we reach 1.5 gigabyte of upload size and 385 megabyte of download size. It's quite a substantial difference, and it's showing that UEFN Cook will drastically reduce the size of an asset. When playing Fortnite, the visual settings will be different depending on the hardware used, and it is especially important when it comes to features like Nanite and Lumen, which will be on or off depending on the console you're playing your experience. On PC, you get more control, and you can switch Nanite and Lumen on or off. Remember that off will be the default status, so make sure you set it up the way you want to visualize your island. So how do you optimize the project size? Well, when optimizing, you always want to go from big to small to have the biggest gain the fastest. And to do this, we need to identify our largest asset. And by opening the project size windows, by default, it will be sorted by type of asset, which is useful, but not so much when it comes to identifying large asset. So what we want to do is, we want to order them by size, regardless of their type. I've got no idea why it's not the default, but hopefully it will change one day. So by selecting by package, you will get a list of all the assets, including meshes, textures, and materials, categorized by size, regardless of their size. And then we can select an asset and directly go into its content browser location, like this air canister static mesh. Now that we have identified a static mesh that we want to optimize, let's start by understanding how to reduce its size. First of all, you want to import a low poly asset, because a lower poly count means a smaller data size. Next, we want to generate optimized LOD inside of UEFN, and we want to simplify the collisions and only use them when necessary, because they will, in the end, add data to your mesh. And then finally, you want to reduce the asset poly count of both the Nanite mesh, the LODs, and the collisions, all of that in UEFN. So it might sound a bit stupid, but remember that a lower poly count in a static mesh means a lower memory size, and that's really critical. So UEFN comes with a panel of tools to remesh your asset and reduce their poly count. In a static mesh, the thing that you want to change to reduce the size are, in the Nanite settings, you want to change the keep triangle % and the fallback triangle %. In the LOD settings, you want to change the % triangles. So as said before, In the 99 tab, the keep triangle percent allows you to remesh the 99 mesh to a lower percentage. And in this example video, firstly, as you can see, I'm swapping the materials to something non-translucent so I can see the 99 mesh wireframe. And then, by lowering the keep triangle percentage, it will reduce the poly count of the 99 mesh to something lower. Still in the 99 tab, the fallback triangle percent allows you to remesh the fallback mesh to a lower poly count. It might sound a bit confusing, but the fallback mesh is also your lot 0 when you're not using 99. If you guys want to know more about the fallback mesh, I highly recommend you checking the documentation because there's a ton to know about it, and it will take me too much time to get into it now. So in video again, first of all, I'm showing the fallback mesh, and then by lowering the fallback triangle, I'll have a lower fallback mesh poly count. So very similar to the 99 mesh and the fallback mesh, you can also remesh the different LODs of a static mesh. And by default, UEFN create 3 LODs. So in this example again, I'm showing the LODs that I want to change, which is the LODs 1. And then once again, lowering the percentage will remesh the designated LOD to a low poly count. You can do this for all the LODs you have, so LOD 1, 2. If you have more than 2 LODs, you can go crazy and remesh them all. Finally, a last optimization trick to do on static meshes is to disable the material collision when you're not using complex collisions. That will get you an average of 10% of data back from that same asset. So here's an example of the size of the air canister imported in Airphoria without any changes. After cooking, this mesh is 2.654 megabyte in download size. And here's the result of the same mesh after reducing its poly count in the detail panel and turning off material collision as shown earlier. We get 0.633 megabyte in download size. So that's a reduction of 70% without changing the visual of the air canister. So let's move on to textures and how to optimize them. So as a rule of thumb, textures are usually heavy assets. So you only want to import them when necessary, and you want to import low resolution textures. Believe me, in most cases, a 512 pixel textures will look as good as a 2K textures. And on top of that, UEFN is limited to texture resolution of 2K. So anything you import above will be reduced. You want to pack your texture using the RGB channels to reduce the amount of individual textures imported. So for example, packing the AO, roughness, and metallic into one OEM map is a standard in the gaming industry. And while keeping a decent size base color and normal map is inevitable, reducing the resolution of the AO, roughness, and metallic will not be as visible. And just like static meshes, it's possible to reduce the texture resolution inside of UEFN. To do this, we'll adjust the LOD bias of the texture, and that will clamp its highest LOD. Alternatively, you can also use the maximum texture size, which will have a similar effect. So once again, after running some tests, by clamping a 2K texture to a maximum resolution of 512, I've managed to go from 0.987 megabyte to 0.66 megabyte of download size. What about MIP maps? Well, simply said, MIP maps are similar to static mesh LODs, but for textures. So by default, when importing a texture, UEFN creates smaller textures to be streamed when needed. Changing the MIP gen settings to no MIP maps, UEFN will then not create these lower resolution textures, and therefore is reducing its project size. Don't go crazy on this, like to do this on no textures, because if you do that, then UEFN will be terrible with performances. So it's for very specific cases, and for example, it's great for background elements or HDRI, because the player will never get close to them, so they never have to be streamed lower resolution textures. And here's the result of disabling MIP maps on HDRI textures, going from 0.393 megabyte to 0.279 megabyte. So now that we had a look at both static meshes and textures, I want to go over some workflow advice to get your project size down. And as said earlier, UEFN comes with a massive asset library from Fortnite, and these assets are very optimized. The great news is that they do not increase your project size when added to a level, making this very efficient. And even though they are stylized and you want to do some realistic environments, they can be very useful to add details in the background. Airphoria was built on this principle, and most of the assets that you're seeing here are actually from the Fortnite library mixed with some custom static meshes. And then finally, let's talk about tileable materials. So as I said before, textures are usually heavy assets, and we want to reuse them as much as possible and to be efficient. The best way to be efficient, without too much of a headache, is to use tileable and world-aligned materials and then add a detail pass with some decals on top. Unique textures in UEFN should only be used for specific hero assets where you don't have a choice. So let's recap on how you can optimize your project size. First, you want to identify your asset and go big to small. You want to optimize your meshes by importing a low poly mesh and reduce the poly count in UEFN. You want to optimize textures by importing small resolution textures, pack them when possible, and clamp the highest LOD. And you want to use Fortnite asset as background details when necessary. And then finally, you want to favor tileable materials over unique textures. So optimizing the project size is quite straightforward. UEFN gives you feedback and control, and that should help you to get under the project size requirements. So I hope that this slide doesn't scare you as much as before. And then when you are reading 400 megabytes, you've got something like this in your head now. Right, let's move on to memory usage. It is our second pillar in our UEFN optimization chart. And the concept of memory usage was first introduced in Fortnite Creative. In short, it is a method for displaying and managing memory across an island. The memory usage is visualized by this thermometer in a creative mode, and the thermometer is limited to a maximum of 100,000 units. Just like the project size, it's only visible after launching a live session. And in simple words, the thermometer is a safety net to prevent overloading a level with too many assets. By limiting the amount of assets, it ensures that the island runs smoothly on all supported platforms and hardware when published in Fortnite. So the memory usage in a thermometer has nothing to do with performances. It just makes sure you're not, crashing a switch when launching Fortnite on it. And the thermometer is quite simple to understand. Whenever you add an asset to a level, it will increase the thermometer. This includes static meshes, devices, and Fortnite asset. And that's the big difference from project size, which completely ignores Fortnite asset. So in this example, by just adding a truck from the Fortnite library, the thermometer went from 3,384 units to 4,780 units. So this truck costs 1,396 units. And the thermometer can be seen as a restriction because you can't increase the 100,000 allocated units, and you can't publish an island if you are above the 100,000 units, making this thermometer your worst enemy the day before content lock. And as you can see here, the thermometer doesn't give you any detailed information on what's big or small in your level. And with this lack of details, it will be very hard to optimize. So we'll use what's called the memory calculation to get a much more detailed result. The memory calculation is only available after launching a live session, and the island will be needed to be uploaded to a private code. This private code, by the way, you can use it to run some tests on different hardware. And after running the memory calculation, you get the detailed memory calculation result in the message log. So let's go through it, but with some video. So first, you want to launch a live session, because as you can see now, the memory calculation is grayed out. So once the live session is up, we then need to stop the game, and then we'll be able to launch the memory calculation. Almost there. Okay, now the game has stopped. Then you can launch the memory calculation. Then you're going to upload it to a private code. You can type whatever you want or nothing. It makes no difference. And then once that's done, the memory calculation will run in the background, and we will get the results into the live session. There you go. But to get a more detailed result, we want to go into the message log, memory test results. And the memory calculation result is a list of the 100 most expensive assets in terms of memory usage in the level. what we need to look at is that you've got the global result, which is the global result of the calculation and the position of the highest memory usage. Next, we've got the name of the asset, then the exclusive asset cost, which is the initial cost for using this asset, the cost per instance, which is simply the cost per duplicate of that same asset, and then the numbers of instances, which is the amount of duplicates. Finally, we've got the total cost of the asset, which is the sum of the exclusive asset, the instances, and the shared asset. So how do you optimize the memory usage? Well, just like the project size, we want to identify your asset and go from big to small. To do so, we will use the memory calculation to identify our biggest asset. And again, similar to the project size, a smaller size asset means a smaller memory imprint. So we want to reduce both the poly count of a static mesh and the resolution of a texture to reduce the impact on the thermometer. So in this example, by a simple optimization pass on a custom static mesh, I've managed to reduce its cost from 9,868 units to 883 units without any drastic visual change. So once again, a lower poly count in a static mesh means a lower memory usage. Next up, we have instances, and they are absolutely a key element when optimizing a thermometer. Instances are a duplicate of an asset which is already being used in a level. They are amazing for optimization because instances of the same object are very cheap. And in this example, this water tank has an exclusive cost asset of 156 units, but an instance cost of 3 units. So yes, these 84 instances of the blue tank are actually cheaper than these 4 units, these 4 assets on the right. And following this concept, to optimize your thermometer, you would delete and replace assets and use the same ones over and over. We've used that a lot in Airphoria, and the tower is the best example between the boxes, the screens, and the scaffolding. Another fantastic tool to optimize the memory usage is the use of HISM. HISM means Hierarchical Instance Static Mesh, and they directly come from the Unreal Engine. For those familiar with UE, it's quite similar to the foliage tool. So HISM allows rendering a large numbers of static mesh instances while optimizing performance by grouping similar instances together and rendering them as a single batch. And even if they are merged into a single batch, HISM still allows you to organize instances based on the camera distance, and that's the difference with ISM. So LODs will still work depending on the distance with the player. The amazing news with HISM when it comes to optimization is that when using them, instant costs will be heavily reduced compared to a regular static mesh instance. And at the moment, HISM are only usable on custom static meshes, and you can't use them with Fortnite asset. So let's go over it by video and how to create an HISM. So first of all, you want to create an empty actor in your level. You can name it the way you want. It has no importance. Then we want to go into the detail panel and add an HISM component. Name it the way you want. Again, it has no importance. Then you want to drag and drop the static mesh. Set it the way you want. Here I'm changing the mobility to something static. And then from there, you can create your first instance by clicking on the plus. You can assign the transform you need. This box was huge, so I just reduced it. And then you can either press on the plus, or you can simply Alt-drag to duplicate that instance. And then if I go back to my actor, if I check my HISM now, you can see that I've made 4 instances. We have absolutely abused this tool to build Airphoria, and everything you're seeing here is mostly HISM. We went as far as replacing most static meshes by HISM, using a custom script in Unreal Engine to batch replace this asset back into Airphoria. We also recreated some Fortnite assets to re-import them as custom meshes and use them as HISM, like these aircon units on the rooftop. So use HISM, they're great. Using HISM is amazing to build large environments. And World Partition is also a great system for making large environments. When enabled in the world settings, it will divide the island into a grid onto the X and Y axis. Cells inside the grid will then be loaded when necessary, and the thermometer will be calculated per cell instead of being calculated for the entire island. So as you can see in this clip, by moving above the city, I go from one cell to another, which have a higher memory usage. So it goes from 100,000 to 50,000. When using world partition, UEFN gives you the option to use HLODs. HLODs are a group of generated and optimized static mesh merged into a simplified static mesh. These assets are then streamed in the distance in cells where the player isn't located. An HLOD needs to be manually built in engine by going into build HLODs. But using HLODs has ups and downs. First, they're really useful because when using world partition, HLOD will cancel the popping effect generated by the cell loading and unloading. They're also great for performance because it creates a very optimized background mesh. And another great thing about HLOD is that you can include or disinclude meshes in your HLOD. So like small props, you can just hide them from the HLOD and that will be even more performant. But the big downside of using HLOD is that because it's basically creating a new static mesh, it will increase both the project size and the memory usage. And another downside of HLOD is that when running a memory test, it will only give you the list of the 100 heaviest assets contained in the heaviest cell. So optimizing will take you more than one memory calculation because you're going to have to go through cell by cell. Another thing to know about world partition is that the grid is only on the X and Y axis, not on the Z axis. So any asset in the same cell vertically will be calculated into the one cell despite being further apart on the Z axis. So in this example, as you can see, the shoe building and the pool on top of it are in the same cell despite being further apart on the Z axis. So having a vertical level will then require planning not to exceed the cell thermometer. And we've had to use some tricks when building Airphoria because of its vertical design. So as you can see here, we split the underground city into another place of the level to avoid overloading some cells. Players will then be teleported during cinematic, giving you the illusion of a continuous world. So to recap on how to optimize the memory usage. First of all, you want to start by enabling world partition or not, depending on the size of the island, and you want to set up your HLOD when necessary. You want to run a memory test to identify your large asset, then optimize your meshes and textures with the same tools as for the project size. You want to replace unique asset with instances as much as possible, and use HISM when possible. Use it. Optimizing the memory usage can get tricky because of the 100,000 strict limit, and that there's a lot of consideration to take regarding your gameplay. But remember, it's a safety net to ensure you're not overloading an island, and it will simplify publishing a good experience to the player. Right, let's move on to performances. It is our last pillar in our UEFN optimization chart, and when talking about performances, I'm talking about the frame rate per second at which an experience is running, depending on the platform and hardware. Fortnite currently runs on most modern consoles and PC, meaning that when publishing a UEFN experience in Fortnite, the FPS will vary depending on what you're playing on. And here's a precise list of all the platforms on which Fortnite is playable. It goes from PC, Mac, PlayStation 5 and 4, Xbox Series X and S, Xbox One, Nintendo Switch, and Android. Performances can be very hard to optimize because unless you have access to all these consoles, it will be difficult to get a full understanding of your island for all the players. On top of that, there is currently no profiling tools in UEFN, making it hard to identify problems or performance bottleneck. Epic is currently working on that, and that will be available in the future. Because of this previous point, out of all the three optimization pillars, it is the hardest one to optimize, and we will rely a lot on our previous experiences. Even though in UEFN is currently missing any proper profiling tools, the engine scalability settings is handy for artists when it comes to optimization. And to simplify this presentation, I'll now call engine scalability settings ESS. So the ESS allow you to adjust the quality of various features in order to maintain the best performance for your game on different platforms and hardware. It has 5 scalability levels, which are low, medium, high, epic, and cinematic. These levels will then gradually improve the visuals by enabling engine features, giving the best performance at the lowest level and the best visuals at the highest level. We can then assign console per ESS, giving us a preview of what an island can look like, depending on the console. take this with a pinch of salt because these are not precise and based on my personal experience. But low corresponds to a Nintendo Switch or Android, medium is a PlayStation 4 or an Xbox One, high is a current gen console such as PS5, Xbox Series X and S and a high-end PC, epic is a high-end PC, and cinematic is just ludicrous with high-end PC for rendering, so that's just something different. To change the ESS, you want to go into the settings, engine scalability, and change into the level you want to visualize. So how do we optimize the performances? Well, with an active profiling tool, we will rely on our optimization experience from the Unreal Engine and use common tricks. So if you struggle with performance, I highly recommend you checking some UE5 tutorials on how to optimize a project because they will be relevant. But these tricks are similar to any game engine, and basically it requires you simplifying lighting and meshes. I also recommend testing as much as possible an island on all available platforms and hardware. The reason for that is that the more you test, the more you can identify where you've done something wrong, like importing a mesh which is super expensive or you've done it wrongly materials. So test as much as possible. So the first thing we want to do is to optimize the lighting. UEFN only use dynamic lighting, so we need to place lights strategically and delete all unnecessary lights. We want to set the lighting's radius of our lights as small as possible and avoid overlapping when possible. We want to set the mobility of every light to stationary to get better performances compared to something like a movable light. Turning off cast shadows on carefully selected lights is one of the easiest performance wins you can get. You can enable or disable cast shadows in the Detail tab. And as a rule of thumb, I will only use cast shadows when the light is drawing sharp shadows in places where the skylight doesn't hit. So this sofa is a perfect example. Whenever you are outdoor, usually disable cast shadows and you get better performances. As a workflow advice, I would recommend lighting a level using the high ESS. That will be your reference point using lumen and the beauty of dynamic indirect lighting. And then from there, we'll use what's called the Lighting Scalability Manager to mimic lumen on lower ESS. And to do this, we'll create different lighting scenario per ESS. So for example, we can add certain lights to the low and medium level, which will not be rendered on the high level, and vice versa. So the Lighting Scalability Manager can be found into the Fortnite library under Lighting Tools. And as you can see in this image from Airphoria, we have made 3 different skylights and created lighting group for both the low and medium level. Next up, in the Lighting Scalability Manager, we have assigned the skylight and lighting group to their respective ESS. And when changing the ESS from low to high, there's quite a big visual difference. And that's because you use different skylights and lights to prioritize performance on low level. It looks completely different. That's because you're using lumen and not lumen, and then we had to really optimize the lighting to get it through. So that's why it looks utterly different. So why the Lighting Scalability Manager is great for your first stroke of your lighting, the Detail mode gives you fine control per light. And it is accessible in the Detail tab under LOD, Detail mode. In this example, setting the Detail mode to high will clamp this light to the high ESS, so it will not be rendered into the low and medium level. After lighting, the next thing we want to look at is static meshes. If an island is under the project size and the thermometer restrictions, chances are that you already have optimized your static meshes. And once again, reducing poly count of a static mesh and reducing your resolution of textures will be better for performances. HISM are back, and yes, HISM are also great for performances because they will unload bulks of objects together based on where the player is. By doing so, HISM will then help with performance and improve overall streaming when traveling across the island. Similar to what the Lighting Scalability Manager does for lighting, the quality level min load do the same for static meshes. When set, it allows you to override the highest LOD on your LOD of choice for every ESS. So meaning that a LOD 3 of a mesh could be your LOD 0 on a low level if you want to. and the quality level min loads need to be set in every static mesh. Exactly like the lighting detail mode, but for static meshes, the geometry detail mode allows you to not render individual static meshes on specific ESS. So therefore, it allows hiding unnecessary details on lower levels, and it is accessible in the detail panel of every static mesh actor. So in this example, by assigning the detail mode of this truck to high, it will not be rendered when the ESS is lower than high. So you can easily hide individual, small props. This truck is a bit bigger for small props, but anyway, you get the idea. So let's recap on how to optimize the performances. First, you want to use the ESS to preview and adjust visuals per platform. You want to test your experience on all available hardware and platforms as much as possible so you can detect problems. Next, you want to optimize your lighting by removing unnecessary lights and disabling unnecessary shadows. You then want to optimize your static meshes, LODs, and use HISM. You want to use the Lighting Scalability Manager to create optimized lighting scenarios on lower-end platforms. And you want to use the level min load to clamp LODs per ESS. Finally, use the lighting and geometry detail modes to hide unimportant lights and meshes on lower-end platforms. So overall, out of the three pillars, optimizing performances is one of the most complicated ones. And in UEFN, because of the lack of profiling tools and the amount of hardware and platforms on which Fortnite runs. But the project size and memory usage restrictions and the performant Fortnite game should help you to a comfortable place. After that, optimizing the lighting is what you can get the biggest win, so focus on this first. And that brings us to the end of the presentation. I hope you've learned something new today, and that optimization seems a little bit more simpler now, and thank you very much for your attention.